first principle involves density in the air which the cylinder as it compares to the air outside of the cylinder. As the flame burns down the tea bag, it heats the air that is contained within the tea bag. As the heat spreads, it causes the air molecules to move more quickly and spread within the cylinder. Then the air molecules inside the cylinder are farther apart from those on the outside of the cylinder, making the air inside the cylinder less dense. And that leads to convection currents. As we explained, the burning bag of tea creates a hot, less dense air, which creates a thermal or convection current. The space created by the less dense air in the outside of the tea bag allows the air to push upwards from the bottom, making the force of the rising hot air enough to lift it in the air.
This experiment is called the Franklin-Bells experiment, and to do it you'll need a few things. First, piece of tin foil. Second, 2 pop cans, one of which has the tab still on it, one of which the tab is removed. Piece of string, tape, 2 alligator clips with wires attached to it. And then lastly, a TV that produces static electricity. This experiment works because you have the TV producing static electricity, which is just the electrons using their voltage, which is the potential energy in an electron. This movement of electrons is what's known as a current. This current flows into the aluminum foil on the TV, and because aluminum and most metals are good conductors, they allow electrons to flow very easily through them. This flow then flows into the wire attached to the foil, which is attached on the other end to one of the pop cans. This pop can then becomes negatively charged because electrons have a negative charge. That means that all other electrons, like the ones in the the little tab, are gonna be repelled away from the negatively charged can, meaning all of the negative electrons are gonna be on one side, and the pop tab's gonna be repelled away. And so, because the other can has protons which are positive, they are gonna attract those electrons, meaning it's gonna move into that one. And once the pop tab and the neutral can, it is neutral because I'm holding it and I'm grounded, meaning that there's no transfer of electrons going on. Once the neutral can has the pop tab touch it, the charges will flow between them, and the extra electrons will flow into the wire, which will flow into me, which is the grounded object, meaning that the charges are going to be balanced, and once they're balanced, they're going to repel each other because like charges repel, and so it's going to flow back towards the negative can, and then the negative can is going to flow, and it's going to transfer all its electrons into the tab, and the tab's going to flow into have its protons flow into the negative can until they're balanced, and then once they're balanced again, they're going to flow back and forth, and then it's just going to repeat the process back over and over, as long as there's a transfer of charges going on.
The potato gun illustrates Boyle's laws, which state that pressure and volume are inversely proportional, meaning as you decrease the volume of the air trapped in between the two pieces of potato, the pressure exerted from the gas increases. This increase in pressure forces the top piece of the potato to exit the tube with force, which goes in depth with Newton's law, starting with the first law, which states an object will stay at rest unless a force is acted upon it, which basically means the top end of the potato will stay at rest unless a force will come through it, which is the PVC pipe. As it pushes it in, it exerts that potato out with force.
The other two of Newton's laws that go with the potato gun are Newton's second law, which basically in this experiment means that the force is being exerted on the top potato because the bottom potato has mass and is accelerating as it's being pushed up the tube. Therefore, it exerts a force onto the top potato. And then it talks about Newton's third law, which says that since the as the bottom potato exerts a force onto the top potato exerts a force, an equal force, onto the bottom potato at the same time. These experiments showed how waves, the different properties of waves, how they behave. Waves just being a means of energy traveling. So like with sound, you just have your mouth or your vocal cords vibrating on the particles in the air, and those particles then collide with other particles, causing them to vibrate in the same pattern until you have particles that go into your ear, and that pattern of vibration that is interpreted by your brain, and that's how we hear sound. And in the first experiment, it shows just some of the behaviors of waves. One being, a couple of just being reflection, which is why you have the particles, the light particles, bouncing off and back up into your eye, which is why you see that image of the window on the surface of the water, because it's bouncing off and coming back, hitting your eyes. Then you have interference, which is when the different waves in the water interacted with each other. You had the peak of one wave reaching the trough or bottom of another wave, causing no wave to meet at that point. And then when two peaks meet, you had the wave being higher than the original, and then two troughs meet, you see them go down lower than the originals. And then in the second experiment, it just showed diffraction, which is when a wave, it goes through the slit, and then instead of just going straight like just a particle would, you have it spreading out and then interacting with each other, and just like the interference, having them meet. And that's why in the center you have the bright white spot, because the two waves meet at their peaks and cause them to be brighter than normal. And then you have the peak and the trough meet and causing the space between the three dots. And that's how waves behave.